It's a pleasure to welcome Masahito Yamazaki for our final talk of the day from IPMU, and he will tell us about discretizations of integrable field theories from 4D Chern-Simons. Thank you.
Okay, great. Thank you so much for the introduction. So it's a great pleasure to present my talk here at IGST. So what I'm going to talk about is based on work in hopefully to appear soon. And we are still thinking about some details, etc. And it's still constantly evolving, but simultaneously, we feel that it's very close to completion. Now, this work is in collaboration with two excellent researchers. One is Mia Ashwin Kumar, who is a postdoc at IPMU, but who is moving to Bern, who will be close to many of you in Europe. And another is Junichi Sakamoto, who is already in Europe at Torino. And it happens that he's also applying for so he's applying for positions in the coming fall, and he's the person who is on site in the conference hall. So I'm attending virtually. So if you try to catch him randomly, please catch him and ask the questions. And okay, so that's about our paper. So now let's begin with the introduction. And the overarching theme of my talk is to try to revisit the very difficult and rich subject of integral models from a different perspective, which in this case is the four-dimensional version of Chern-Simons theory. And this is the approach I have been pursuing, and in particular with the paper with Kevin and Edward. And it's also worth mentioning that some aspect of it has been studied in a different language in terms of the Fine-Gordon model, in particular, Bernard Bicedo and his collaborators. And which in my language is the Hamiltonian formulation of 4D Chern-Simons theory, as later understood. Now, what is the 4D Chern-Simons theory? Well, it's similar to standard 3D Chern-Simons theory, but with some extra features. So there is this 3D Chern-Simons now, which is the standard term, but then it's wedged with a holomorphic one form, which for the purposes of my talk, for the most of the part, it's actually just dz, where z is the complex coordinate along the two of the direction of the four dimensions. And so because of dz, there's only three components of connection, but otherwise it's almost like a 3D Chern-Simons, except that the geometry is of the form two manifold times two manifold. And the sigma part is the part where you get the two-dimensional, integrable field theory in my story. And the C is the part which geometrizes the spectral curve, spectral parameter of the integral model. And in a sense, the approach to integral models from 4D Chern-Simons, it's a precise analogy to understanding knot invariance from three-dimensional Chern-Simons theory. Now, what is nice about the story is that you can try to enrich the story by incorporating the defects. Well, there can be different defects, as I'm going to explain. But let's see. So let me start with the two-dimensional defect, which fills the whole two dimensions where the integrable models live, which was sigma, and which means that they're like a point like on the spectral curve, which is this C. And so they are located at a particular coordinate. So z equals z1, z2, etc. And different type of surface defects can be located there. Now, this is a four-dimensional geometry, and it is a four-dimensional theory coupled to defect theory, which are two-dimensional. So it's a coupled 2D, 4D system. But you can try to integrate the theory along the spectral curve. And then what you get is the two-dimensional effective theory. This is the theory you might be familiar with. That this is the theory, integrable quantum field theories, which we tend to discuss in the integral model community. And so it's a 4D, 2D coupled description is just another description. But the nice thing about it is that there's a four-dimensional gauge field whose equation of motion simply says that it's a flat connection, essentially. And this ensures that there is associated flat connection, which is a Lux connection down in the 2D. So it automatically ensures the classical integrability of the theory. And then you can try to quantize the 4D coupled system, and you might hope for quantum integrability. Although not all the aspects of that is understood, but at least classical integrability is ensured from this construction. So to just give you a simple example, we can try to have two defects, where each of the defects is just a free fermion, and chiral fermion and anti-chiral fermion, and then it couples to the different components of the gauge field, Z component or Z bar component, and let's see, and Oh, sorry. Let's see. Sorry, not the Z component. Sorry, W component. The other component. There was a typo here. And let's see. So there's a chiral and there's a chiral fermion, the antichiral fermions. They are separated in the spectral curve. But they can try to, so without the 4D Chern-Simons gauge field, they are separated completely. They don't talk with each other. But there is a propagator for the gauge field. Sorry, this is W again. So and then there's a propagator, and then they communicate with each other via the exchange of the gauge bosons. And then that's how you get the Lagrangian. And the interaction term comes from the JJ bar. So the gauge field couples to the current, and there's a JJ bar deformation, and then there's a 4 Fermi interaction generated. So that's how you get the Teeling type models. So let's see. So this was the story. Now the question is to, well, we're going to discuss the 2 questions which we want to address in this particular setup. The first question is to how to discretize integrable quantum field series into the lattice models. So here on the left, we have an integrable quantum field series, and it discretized in the lattice model. And so if you want to go back, you can take some dynamic limit. And of course, this has been discussed quite a bit. And as far as I know, this was actually one of the motivations, historical motivation for thinking about integrable models at the outset in the 80s or so. But I want to, and then there are a lot of examples. Well, there are some examples discussed in the literature making the connection, but we want to do this discretization procedure systematically. And this is not completely trivial because we have to discretize, preserve integrability. And also, from more physical standpoint, this is about the relation between UV physics and IR physics. So it involves RG flow. And this type of question is relevant in many questions in statistical mechanics and condensed matter physics, for example. Now, the second question is how to describe the duality between integrable quantum field series. So there are different dualities, different descriptions of the same physics, as in the, for example, non-abelian bosonization. And so there are, the question is how to embed these type of bosonizations and dualities into the 4D Chern-Simons framework. So that's question 2. And a priori, it looks like that these 2 questions are completely different questions. Just how to discretize and how to discuss the dualities of integral quantum field series. And there are different questions, but it turns out that there are some connections, as we will discuss. Now, let's see. So then let's see. So how to discuss this discretization procedure or the duality between defects, the duality between integral quantum field series. Well, the basic philosophy here is to stick with the 4 dimensions in a sense. So here we start with the usual 4-dimensional integral field theory. But from the viewpoint of 4-dimensional theory, that's a kind of effective description, which is obtained by starting from 4D theory coupled with 2D and integrating along the surface defects. And so you can try to discuss everything either way, but there are some advantages of starting with the 4-dimensional description. And one of the reasons is that the surface defect series tend to be very, very simple. For example, in this case, in this example, you have a Teeling model, which has interaction term, etc. But here, the surface defect theory itself is a free theory, really free, just coupled to the external gauge field. So it's a very simple description. And another thing is that it can be much more general. And one of the reasons is that if you start with this description, here we have a one chiral defect, another anti-chiral defect, and obtain the Teeling model. That's one theory. But once you understand this, you can try to include multiple such defects. For example, 2 defects, 3 defects, etc., and you immediately obtain some generalization of the Teeling model. So by studying everything at the level of the defect, you can try to be general and discuss not just a single theory, but a class of theories simultaneously. And because of there is such an advantage in discussing the defect, the strategy is very simple, actually. Just to take the surface defects and try to discuss discretization and dualization, etc., intrinsically at the surface defect level. So said this way, okay, so the basic answer to the question number 1, how to discretize an integrable field theory, well, the answer is very simple. You basically discretize the 2-dimensional defect into 1-dimensional defect. For discretize each of the defect in 1-dimensional defect. And since we start with a 2-dimensional defect, we get a 1-dimensional defect. And of course, the question is what these defects are. So you can line down the defects and you obtain the lattice. And the question is, okay, so what type of integral lattice model we get? And it turns out that there are nice geometric arguments which converts this one-dimensional defects into Wilson lines, and Wilson lines are known to generate the integrable lattice models associated with the Yangians and their quantum affine elliptic generalizations. So we know what type of integral models it gives rise to. So the end result is that we get the standard spin chain. So we know we have the relation between two-dimensional defect and the discretized spin chains. And interestingly, there is a huge degeneracy in this description because there are a lot of different two-dimensional defects giving rise to the same spin chain, which is partly because the spin chains are governed by the symmetries like Yangian and the representations. Now, what about the dualities among the defects? What about the dualities between integrable quantum field series, like a bosonization? Well, the idea is, again, to try to start with some dualities among the defects themselves. So here I have a schematic picture where one two-dimensional defect is converted to another two-dimensional defect. So this is self with a statement of 2D duality. For example, you can invoke some version of the 2D bosonization, but a much simpler version for free field, basically. And then once you have that, you can try to apply the bosonization or some duality for each individual surface defect. And here in this example, we have two surface defects, and you can take apply the duality for each of the defects, which means that we have not just a single duality, but we actually have 4 duality frames. So we have a chain of dualities, so which we call the duality web. And here we start with the case of the one duality, and they have 2 defects. But for example, we can have 4 defects, for example, and we have 2 to the power 4 duality frames. And in fact, we can also discuss the triality of the defects, and that even gives rise to even more rich class of dualities between integral quantum field series. So that is the basic structure. So okay, so I have been asked to give an overview part, and this is the end. So I should pose some questions, I think. Any questions? Okay, well, if not, I can proceed. Yeah, so let's see. So let's work out the discretization part. Let's see. So okay, so before starting the discretization, let me a little bit more specific about what type of defects I consider. Oh, sorry, there was a typo again. So the gauge field components W, the other components, and the W and W bar. So we consider chiral and antichiral surface defects. And I consider the type called the order defect. So there are disorder defects and order defects. And disorder defects and order defects are different in that order defects have their own degrees of freedom. So they have like a 2D Lagrangians, and they couple to the 4D Chern-Simons series through interactions. Whereas disorder defect, there is no localized degrees of freedom per se, but it just imposes singularity of the gauge field. So here I consider order defect, which means to have some Lagrangian. For example, this is a S2D, so it's a Lagrangian of the defect itself. And there's a Lagrangian of the 4D Chern-Simons series itself. And then it couples through the current of the 2D defect. So the assumption is that the current has a global symmetry G, which is a global symmetry, and then hence there is a current. And you can try to couple it to 4D Chern-Simons series gauge group, the same gauge group G, by this standard combination AJ. There could be other terms, but it at least involves AJ coupling. And there can be multiple defects here. And plus and minus represents the chiral antichiral component, and it couples to W and the W bar component of the gauge field. So W and W bars are the directions along the integral field series. Integral field series are live in the curve, which I denote by sigma, which has coordinate W and W bar. So this is the setup. And once we have the setup, we can try to integrate the theory along the C. And here I have a little bit more explicit description. Here you have a Lagrangians with the chiral defects, antichiral defects, and then the JJ bar deformation leading more generally. And here I have the expression of the classical R matrix. And this depends on the difference between the coordinates. So each of these defects is located at the point in the spectral curve, and there is that appears as a parameter, like a coupling constant of the theory. So the coupling constant, which is the parameter of the effective two-dimensional theory, is geometrized into the coordinates. Okay, so this part is not new. I just said what was known before. But this is a setup, and we have the Lagrange. The point is that I'm not going to be too explicit about this Lagrangian because the formalism is completely general, and I'm going to keep discussing the defects. But you should have in mind that there's explicit Lagrangian like this in everything I say. And this is a 2D effective Lagrangian, but you can also write down the Lux matrix, for example, by for the 4D Chern-Simons logic. And because the Lux matrix, Lux connection is simply the gauge field connection of the 4D Chern-Simons. Now, okay, so let's start with the chiral defect. And again, sorry, this is the bar direction. So bar and Z bar, W and W bar direction. So you have a chiral defects and anti-chiral defects. And you're going to discretize. And the discretization itself is actually simple. So here, for example, it depends on the W bar coordinate. And when you discretize, so it depends on one of the coordinates of the two. So that's what I mean by chiral defect. So when you try to discretize, you discretize it in the other direction. So it has a W bar derivative, and you try to discretize the W direction by simply replacing the integral by Riemann sum. And you have the discretized action for each of that is one-dimensional fermion. And you have the same thing with the anti-chiral defect, but this is a derivative appears in the W direction, not in the W bar direction. So when you discretize in the other direction, like a transverse direction. And when you combine, you get the light cone lattice of defects, where each of the defects is one-dimensional, and depending on whether it's chiral or anti-chiral, it spreads in different directions. And of course, this is the integrable light cone discretization, known since the 80s or so. Well, it's studied most intensively by Desprez-Vega, a remarkable set of papers. And they are also, Fadeev and collaborators have many related papers. So this itself was known. And let's see. And then you can try to discuss the relation between the integrable structures afterwards, after the discretization and before the discretization. I'm also tempted to say that this is also, there is some extra motivation to study these theories. So here we are talking about the integrable, integrable quantum field theory and discretized. That's the way we say. But we can also regard this as a way of a time evolution in the Floquet system of quantum or integrable totalization, which some people, including myself, have studied recently. Now, okay, so here we discussed the discretization in the case of one chiral defect, one anti-chiral defect. But you can try to discuss the multiple surface defects. For example, here you have 3 chiral defects, the one that is filled in, and also 3 anti-chiral defects, which are represented as points with nothing filled in. And in this case, there are 3 different types of defects spreading in directions in one of the directions, and 3 other anti-chiral defects in spreading in other directions. And in these cases, there are some choices to make. You can try to change the order of the lattice by permutations, but they should flow back to the same theory. So these are two different generalization, discretization of the same integral field theory, but we believe that it flows to the same fixed point. Now, and here in this case, there are 3 different types of chiral defect, and in those cases, they are going to be inhomogeneous lattice. So we're going to get the inhomogeneous lattice, and as you see, it turns into inhomogeneous spin chain. And the inhomogeneity parameters are parameters associated with the location of the surface defects. Okay, so this is a discussion, and here I used a very explicit Lagrangian of the theory. I have a very explicit Lagrangian of the theory. Well, here, but we can try to be much more general, actually. For example, here's an example. So suppose that I don't even know what the Lagrangian is, but of the chiral defect is, but I know that it's a chiral and it's a massless. So in those cases, so it's a conformal field theory, essentially. So in those cases, it's a chiral half of the conformal field theory, and mathematically it's described by a vertex algebra. So we can be more abstractly discuss the vertex algebra as a defect. And there are certainly many examples of that. Well, of course, we have to assume something in order to couple it to 4D Chern-Simons. And previously, the assumption was there is a G symmetry, global symmetry G, where G is a gauge group of 4D Chern-Simons. And there's a counterpart of that, which is that we have this vertex algebra contains the current algebra of G associated to level K, some level K. So that is the assumptions. And we can start with this assumption and then include that as a defect as well, if you like. Well, we can try to be even more general by considering C4 vertex algebras, but I won't say too much. Now, okay, so how does the discretization work? Here we don't have a Lagrangian, so then how we even discretize it? Well, there is actually something of help in the mathematics literature, and that is the procedure is known as so the end result is known as the Zoo's algebra. So Zoo's algebra is essentially the reduction. In this language, it's a one-dimensional reduction of the two-dimensional theory. So the two-dimensional defect is described by vertex algebra, and so vertex algebra is described as a set of operators together with the operator product expansions. And the one-dimensional version of Zoo's algebra is just to take this zero mode, one of the components, and then OPE is translated in some associated product in this set of operators, O0, which is one of the components of OW. And so this is known as the Zoo's algebra. It's a well-defined mathematical concept, and for many vertex algebra, you can discuss it. There is explicit formulas, etc. And so, and before I assumed that there is a current algebra, and then it goes to the Zoo's algebra for the current algebra itself is a Lie algebra essentially. So that's how you get the usual Lie algebra, and which we expect to be present because we are talking about the folding Chern-Simons with gauge group G. So, okay, so by following this procedure, okay, so you either by Lagrangian, for example, or you can try to be more abstract formalism, vertex algebra, etc. You can try to discuss discretization of a lot of stuff, many different type of defects. So the free chiral fermion defect, chiral anti-chiral fermion defect, this is the one defect which I discussed before. You can also discuss so there's I think it's correct. So what we call the coadjoint orbit defect. I don't know if it's a good name or not, but it's basically G inverse DG. And for G is a group valued, and it couples to the connection. And then there is a lambda, which is the highest weight. And so this is the defect. We can also have a Boson kind of a ghost version of the beta gamma version of the chiral fermion beta gamma defect. And you can also discuss more general beta gamma system whose target space is a Frag manifold, for example. So in this case, it's not just so it requires a sophisticated procedure. You start with if the target space is known to your manifold, it's a manifold. So it's obtained by gluing the coordinate patches, and then each coordinate patch there is a beta gamma system which are glued consistently. So these are the different things. And it turns out that in one way or another, there are some fine points, but one way or another, after the discretization, they're all related to the Wilson line in some representation. And this goes by the name of Borel-Bot in the mathematics literature. And the rough idea is as follows. So here you start with some Lagrangians. So let's take some Hamiltonian fermions, etc. And you discretize, and I said that I obtained some one-dimensional quantum system. And the question is what? What is that? Well, okay, so what is there's a mathematical content of that is that the one-dimensional quantum mechanics means that there's a Hilbert space together with the action of G, because we assume that there is a symmetry G. So there's a Hilbert space and there's a representation of G by using the Hilbert space. So that's known as a geometric representation. And basically you keep track of what type of representation content there is. And then you can convert Wilson lines into some of these defects into Wilson lines. And the similar thing has been discussed, for example, in the 3D Chern-Simons, and the Wilson line is converted, for example, to this coadjoint orbit defect in that context. And so what's important is that although there are all these different things, but they are in many cases, not completely, but in many cases related to the Wilson lines. And once we know that it's a Wilson line, we can relate it to the standard spin chain. So what we are noting here, etc. Previously it was abstract line, but now it's just the usual spin chain associated with the Wilson, associated with Wilson lines of the folding Chern-Simons theory. And in fact, Wilson line is connected to so many different things in the different representations. Well, of course, depending on which defect you consider, you land on different representations. So not everything is the same, but sometimes they land on the same Wilson line. So they are converted to essentially the same integral model. And so that is a degeneracy statement. And you can try to, so this was a statement about defect itself. But you can try to, for example, consider one chiral defect and another chiral defect and see what type of series we get. And so this is an example. So if you start with the coagent orbit defect, you get the so-called Faraday-Freshetigy model. And then you start with the beta gamma of fermion, then you get the Thieling model. So they are all related. So this was already an example of the statement about the dualities, but we can try to be a little bit more systematic as to how to discuss the dualities. So that was the topic number 2. And this slide I already showed you, but the point is that you start with a C duality, what I call the C duality among the defects, and then that will spit out as a byproduct of the 4D Chern-Simons realization a web of dualities. So that was the point. And of course, the question is now, what C duality are we going to use? Now, let's see. So, okay, so what is the C duality? Well, one of the C dualities we can use is the duality between free fermions and the West-Middle-Witten model. So here it's a free fermion, no interactions. And it just couples to the background gauge field. And here, assume that the background gauge field has components only in the chiral direction, but not in the anti-chiral direction. And then there is a both statement of bosonization that this is mapped into West-Middle-Witten model. So here's the West-Middle-Witten term, and there's a current, and there is a coupling of the current to the background gauge field, which you regard as one of the components of the 4-dimensional gauge field. So free fermion turned into WZW, and then basically the statement is that okay, so since we can use this, so we can have a fermions and WZW. So you start with a fermion anti-fermion, giving rise to Thieling, but then you convert everything to West-Middle-Witten model. That's this description. But you can also convert part of, for example, only half of the defect into West-Middle-Witten model, and while the remaining half is fermion, etc. So logically, all these duality statements should hold. Now, there is one fine point, which is that okay, so which we haven't taken into account, that these theories have anomalies. And in fact, anomalies are crucial because, in fact, the derivation of this duality itself heavily relies on anomalies. And okay, and the anomalies for what? Anomaly for the symmetry G, which was a global symmetry from the viewpoint of two-dimensional theory, but we are gauging when we couple it to 4D Chern-Simons. So we have to make sure that these anomalies cancel. Fortunately, there is a way to cancel the anomalies, and so the anomalies are, first of all, localized as defects. So anomalies come from the defect, so they are localized at the position of the defect at the particular point in the spectral curve. And then now they can try to cancel this anomaly from the anomaly inflow mechanism. And there isn't too much in the 4D Chern-Simons theory, but you can also try to change the form of the one form, holomorphic one form. Yeah, so this was what I was discussing with Kevin, but some of the things didn't appear, and it was also explained some other papers, including the paper, this paper by Gaoto et al., for example. And let's see. So the point is that you can make the holomorphic one form itself. Previously, it's just a DZ, but you can try to make it position dependent, and with the poles to the one form. So there's one of a Z type of singularities, the one form. And when you have D, you have a del bar acting on this, giving rise to the delta function, which cancels this contribution from the defects. So there's a nice way to cancel the anomaly, and this type of mechanism works. So this is a new holomorphic one form, and you need to make sure that there's no poles at infinity, and then that puts the anomaly cancellation condition. And so K plus and K minus are the levels of the defect of the current algebra associated with the chiral and anti-chiral defects. So this basically is a very intuitive. Basically, the anomaly is cancelled between contribution from chiral parts and anti-chiral parts, and this is the global constraint. So which means that so this statement about the bosonization is still true, but the constraint is you have to make sure that the anomaly is cancelled. So for example, if you're including one fermion and another anti-chiral fermion, it's okay to have the same type of representations. But if you try to talk about insert the fermions in a different representation, etc., you have to be more careful. Now, so this is the statement of bosonization, and in our paper we're going to be more explicit about with the formulas, etc. But this actually raises one interesting question, which is that this holomorphic bound form has a pole, and so it has a pole, and whenever it has a pole, we should try to compensate that by imposing the condition of the field to make the action basically finite. And this is so this should be chiral Dirichlet condition. Oh, sorry, again, this is W bar on the gauge field. And so this type of thing you can let's see. So perhaps I can go straight to here. So there is a condition on the gauge field which I call the Dirichlet boundary condition, like a Dirichlet defect, Dirichlet boundary condition. But you can also regard it as a defect as well. And the interesting statement is that we discussed the duality statement between bosonization fermions to WZW. So that's the statement bosonization. And if you look at the derivation of the bosonization, you go through something in the middle, which is the theory obtained by integrated fermions and integrated of the gauge field. And then there's yet another description in terms of the Dirichlet boundary condition, which can also be related to this description. So there are actually a zoo of different descriptions of the same physics, and then this is just a single defect. Then you can try to incorporate that into the spectral curve and many defects, and then see what we get. And I think it's so. Well, let's see. So we are checking some of the statements, but it seems that if true, this gives rise to a huge web of dualities, new bosonizations. Yeah, so it seems that I have a few more minutes. So I can spend a little bit on how to discuss at the level of string theory. And I won't say much, except first of all, the whole setup can be embedded to string theory. And for example, the 4D Chern-Simons theory can be realized by D5 branes on omega background. So D5 brane 6-dimensional theory, and you put in the omega background, which is to 3 directions. And the rest is sigma times C, which is the 4-dimensional Chern-Simons direction we have been discussing. And now you can try to discuss first the Wilson lines. And the Wilson lines are realized by defects, 1-dimensional along the sigma directions, and then spreads out some other direction. It's a point like in this C. And if you want to realize the Wilson line general representation, you should have multiple such defects, such these 3 branes. And there is a way to cook up a general representation by regarding as a collection of bosons or fermions by looking at the Young diagrams from 2 different directions. And which is it's a topological fitted version of some of the discussions in the 4D NCO4 super Yamels. And now we can try to use this to try to connect the stories to a lot of different stuff. Not everything, we haven't discussed too much so far, except that at least one thing we can discuss already is that, so previously we discussed the procedure of starting with the integral field theory and how it discretized the lattice model. So here I have the Wilson line already. So we can try to go the other way around. So namely start with the integrable lattice model and take the sum of the limit, and you should get the integral quantum field theory. And for example, so this, let's focus on one of the defects. So plus or minus is just spread in different directions. So plus, for example, it spreads in 0 direction. So one dimensional line in the sigma. And when you take the sum of the limit, you expect it to turn into a surface defect. So it should fit in the 1 direction as well. But it turns out that D3 branes turn into not the D3 brane, D4 brane, but to the D5 brane with 1 extra directions included. You can convince that by just checking supersymmetry, for example. And so physically, this can be understood as a version of the Myers effect, where so you start with the D3 branes, and then it's located at a particular point along. So it's discretized, but then try to make the charge. We have many copies of the D3 branes, and we have the charge, and it grows up into supertube. And in the limit where the charges go to infinity, in the sum of the limit, the supertube decompactifies, and then you get the D5 brane here. So this gives another intuitive picture for how the discretization procedure, and also the opposite, the sum of the limit, happens. Okay, so this is the end of my talk. So so we discussed the 2 questions. One is how to discretize integrable quantum field series into integrable lattice models. And so we basically we start with the 2D defects and it's turned into 1D defect, each of which describes the simple quantum mechanics. And by taking advantage of geometric quantization, it can be converted to Wilson lines, hence making the connection to integrable lattice model clearer. Now, along the way, we also discussed degeneracy in the description, which is the statement about the dualities. And you can try to discuss the dualities simply by invoking the dualities of the defects. And this raises a lot of questions, most of which we haven't answered yet. But at least it gives us a statement about the huge web of two-dimensional dualities about integral quantum field series. And here, most of the discussion goes through at the defect-wise, but there are some important global constraints on the spectral curve, which comes from the anomaly cancellation condition. Okay, I think time is up. Thank you.
Thank you, Masahito. Any questions?
So your anomaly cancellation condition was basically this pole at infinity going away?
Yes, that's right. Yes.
So why is this so important for you? I mean, because you introduced poles at a bunch of other places. So why no pole at infinity?
Yeah, I mean, you can try to have a pole at infinity, but that just means that it's included. So it exists that there is another defect there. So and so what this means is that you can try to if the anomaly cancel what this means is that if the anomaly cancellation is not satisfied, you can cancel the anomaly by including an extra defect at infinity. So that's a sure. Yes. So that's the statement. So here I'm discussing the situation where I have all the defects already under control, already tabulated. And but if you like, you use a change of variable. I have assumed that all the defects are located in a position other than infinity. So in a sense, that's just the input in a sense.
Okay, thanks.
Any other questions?
Sorry, Masahito, might be a side question. When you're describing this, all possibilities of going through the chiral field and the beta gamma work yes. systems, I'm just wondering is it possible for you to consider, is it understood, if you consider superchiral field with a JJ bar deformation where these moment maps are also supersymmetrized? So is it clear what it would mean at the Joule's level at the 1D defect?
Yeah, let's see. So, well, yeah, I mean, because some aspect of that, yes. Yes.
The second point that you understand, all these anomalies also would disappear immediately.
Well, let's see. Yeah, I think, well, right. So the supersymmetric cases, so there are like a supersymmetric defects. Well, one trivial comment is, of course, it's a special. So here, I think that's the supersymmetry. So it's a special case of that construction. So as long as the global symmetry G exists, for example, so that's incorporated. But perhaps the question is that whether you can really take advantage of that, as you said, as in anomalies, etc. And yeah, so well, okay. So probably that means that it's a special example, but it gives us more flexibilities, I guess. And it might help the story. For example, here, what's complicated is that the anomaly cancellation condition should be satisfied, which is, of course, what you expect. It's like a Gauss law on the surface. But for example, you might be, remember previous paper with Kevin, we discussed, for example, cutting the Riemann surface into two, for example, and things like that. And when you do that, of course, the global constellation might be, anomaly cancellation condition might be messed up. So typically, when you try to cut up, there's extra singularity you have to take into account, etc. So that causes an extra complication. But it might be that if you restrict the defect to the situation, and then some things might simplify. And right. And another possibility is that it might be of help in understanding the realization from string theory, for example. So yeah, I mean here, well, what happens is that usually you start with supersymmetric multiplet because we have an embedding in terms of of course, everything is Lagrange, etc. So we have a supersymmetric situation. But then when you put it on omega background in here, it loses some of the components and you get the bosonic degrees of freedom, which is the one we are talking about here. But in the situation you're talking about, you have something, and then there is supersymmetry, but that supersymmetry part remains even after the turning of the omega deformation. Sure. So yeah, so how to understand, put that into perspective here, because in the most of the transport selection, you have omega background term known here and there. So a lot of things seems to go away, and how to incorporate that into the string theory picture. That sounds like another interesting question.
Mm-hmm. Okay, maybe just a very quick point regarding what you mentioned the supertubes. So I think another interesting case there is that when you are taking this the compactifying limit, but you can put also a background where your supertube, your R goes to infinity, but you balance this by a certain background, like at a flux. So yeah, it does not decompactify. I'm just wondering what would it mean in your setup? Do you know?
Well, let's see. Yeah, so I think that yeah, indeed, that's there's essentially like an electric magnetic flux, and then it generates angular momentum, stabilizes. Yeah, so that's what they discuss. And our understanding is that if you take the close to the thermodynamic limit, but like a finite number of D3 brane, and that's a situation where you have the finite radius super tube, and
right,
so
that's a possibility.
Yeah. So I think the connection to super tube holds at the at the finite radius, and that corresponds to so in a sense, the radius itself is in the like RG parameter when you flow from the lattice model to the integrable quantum field theory. That's the picture.
Okay, all right. I'm just saying that in this regime there are also interesting Sleptonic properties.
I see. Yeah, that's very interesting. So it might mean that it might mean something like integral quantum field theory on a circle or something. Yeah. Let's see. Well, it's not quite a circle, but some aspect of solitons remain after discretization. Something like that. It sounds like a very interesting possibility. I see. Thank you.
Go on. Yeah.
Maybe one quick question. So your new omega effective now it has poles, but it also has zeros. So it means you
yes
disorder defect.
Yes.
So the duality mixes order and disorder then.
Well, yeah. So that's an interesting statement, and I don't have a final word on that. First of all, in the discretization procedure, for example, we didn't discuss the disorder defect. We just presented, but as you say, correct? They say this generates the disorder defect. So it actually accompanies the disorder defect. So this shows that there's at least a close connection between disorder and order defect. Now, what accompanies the duality limiting? And that's something we're trying to understand still in gross detail. But at least it seems that that's some extra ingredient coming to this construction. For example, if I said that Dirichlet defect, for example, here, but that's only I'm talking about the poles. But you should also talk about the zeros and the disorder defect. So the correct statement is the Dirichlet defect plus disorder defect. That's the whole thing. It generates the F1 form. And then it corresponds to the quantization of the free fermion. And roughly speaking, so if you try to quantize, there is a pair creation of the poles and zeros of the one form. And so it accompanies the disorder defect. And the hope is that my hope is that this is of help in understanding the quantization with the disorder defect included, and hence to discuss more general non-orthogonal field series. But but I don't have a final word on this yet.
Yeah, thanks for the answer.
That's great, thank you. In view of time, I propose that we move any further discussion to the discussion hubs. And then before we thank Masahito again, after we do, there'll be an announcement. So let's thank Masahito.
Thank you.